Hello. In this video, we'll work out an example about Taylor polynomials. We're given the function f of x is 1 over 1 plus x, defined for all x except for x equals minus 1. We're going to find the fifth Taylor polynomial for f about a equals 1. And then we'll use this to approximate f of 2. Now recall that for a natural number n, the nth Taylor polynomial about a equals 1 is given by this expression. F of 1 plus the sum k ranging from 1 to n, kth derivative of f at 1, x minus 1 to the k over k factorial. And recall k factorial is 1 times 2 times 3 all the way up to k. Now, in our case, n is equal to 5. So we're dealing with a polynomial p5 of x, which is f at 1 plus first derivative at 1 over 1 factorial x minus 1 plus second derivative at 1 over 2 factorial x minus 1 squared plus third derivative of f at 1 over 3 factorial x minus 1 cubed plus the fourth derivative of f at 1 over 4 factorial x minus 1 to the fourth plus fifth derivative at 1 over 5 factorial x minus 1 to the fifth. So what we have is p5 of x equals f at 1 plus first derivative of f at 1 x minus 1 plus 1 half second derivative of f at 1 x minus 1 squared plus 1 over 6 third derivative of f at 1 x minus 1 cubed plus 1 over 24 fourth derivative at 1 x minus 1 to the fourth, and the last term 1 over 120 fifth derivative at 1 x minus 1 to the fifth. So in order to get an explicit expression for p5, we need to calculate the derivatives of f up to order 5. So f is 1 over x plus 1, so the first derivative is minus 1 over x plus 1 squared. Second derivative is 2 over x plus 1 cubed. Third derivative is minus 6 over x plus 1 to the fourth. Fourth derivative 24 over x plus 1 to the fifth. And lastly, the fifth derivative is minus 120 over x plus 1 to the fifth. Right. Now we need to evaluate all these expressions at a. Now in our case, a is equal to 1. So we need f at 1, which is a half. We need first derivative of f at 1 minus a quarter. Second derivative of f at 1, 2 over 8. third derivative of f at 1 minus 6 over 16, fourth derivative of f at 1, 24 over 32, and lastly the fifth derivative of f at 1 minus 120 over 64. So that should be to the power 6. Right, now we can write down an explicit formula for P5. Right, so we have the values of the derivatives, and we have this formula which we wrote down before, and now we just need to plug in the values of the derivatives. Right, so what have we got? We've got P5 of x is f of 1, which is a half, plus first derivative of f at 1, which is minus a quarter, x minus 1. Second derivative of f at 1, 2 over 8 times 1 over 2 x minus 1 squared, minus third derivative minus 6 over 16, 1 over 6 x minus 1 cubed, plus 24 over 32, 1 over 24 x minus 1 to the fourth, minus 120 over 64, 1 over 120 x minus 1 to the fifth. Right, so we simply plugged in the values for f, its first derivative, second derivative, third derivative, fourth derivative, and fifth derivative into this expression. And what comes out is everything cancels out rather nicely in this example. 1/2 minus a quarter x minus 1 plus 1 over 8 x minus 1 squared minus 1 over 16 x minus 1 cubed plus 1 over 32 x minus 1 to the fourth minus 1 over 64 x minus 1 to the fifth. Right. So there we've got the fifth Taylor polynomial for our function f about x equals 1. Now let's use this Taylor polynomial to approximate f of 2. Now, f of 2 is approximately equal to P5 at 2. And we can calculate P5 at 2 explicitly. So that is 1/2 minus 1 quarter 2 minus 1 plus 1 over 8 2 minus 1 squared minus 1 over 16 2 minus 1 cubed plus 1 over 32 2 minus 1 to the fourth minus 1 over 64 2 minus 1 to the fifth. Let's just make a bit more space. Right. So this is 1/2 minus 1 quarter plus 1/8 minus 1/16 plus 1 over 32 minus 1 over 64. Right, and if we add the fractions, we put it all over 64. It's 32 minus 16 plus 8 minus 4 plus 2 minus 1. That's going to give us 21 over 64, and if we write down the decimal expansion, we get 0.3281125. Right. Now, how good is this approximation? Well, f of x is 1 over x plus 1. So we can calculate f at 2 as 1 over 3. And 1 over 3 is just 0.33 repeating. So we see our approximation is accurate in the first decimal place. But in the second decimal place, we have a discrepancy. Now, if you were to calculate the Taylor polynomials for different degrees, n, then we get this table of values for p of 2, for pn of 2. Right, so we've calculated now p5 of 2. You see, if we go 1 degree higher, we get p6 of 2. Now we're accurate to the second decimal place. We carry on and we take p8 of 2. Now we're accurate to the third decimal place. And now if we wait a little bit longer, up to p12, now we're accurate up to the fourth decimal place. And if you go further, even further, and you look at the 28th Taylor polynomial, then you're accurate to 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places. Now, calculating p28 at 2 by hand seems like a daunting task, and it is. But for a computer, this is a very simple calculation. Okay. So, this example is a nice illustration of how to calculate Taylor polynomials, and we see here how they can provide accurate approximations for function values. Of course, this particular function, we can calculate the function values quite easily without resorting to Taylor polynomials, but for other functions, for instance, if we look at, say, f of x equals cosine x, then the Taylor polynomials provide a good way, at least for a computer, to find approximate values for this function.